The only junk DNA is in my colleagues' brains.
Today we're featuring Craig Venter, a world-renowned biotechnologist known for his groundbreaking contributions to genomics. He had a pivotal role in leading the first draft sequence of the human genome and assembling the pioneering team that achieved the transfection of a cell with a synthetic chromosome.
Cells are very dynamic, changing second to second. But one thing is fundamental to all life, and that's the genetic code.
Later in life, he and his research team created the world's first synthetic organism from scratch, demonstrating the potential of synthetic biology to engineer life at the molecular level.
Taking those gene pathways, putting them in synthetic organisms, we'll be able to create whole new chemical libraries.
Craig's a leading figure. He's hilarious, unfettered, unshackled, and unafraid. You'll hear all of that in this episode and find out why he was among Time Magazine's 100 most influential people in the world. Not once, but twice, maybe on another planet where life already exists. So without further ado, we welcome a lively episode of the Into the Impossible podcast. My friend Craig Venter, live, recorded at UCSD this past fall.
Welcome everybody to what promises to be an exciting and lively, emphasis on lively, episode of the Into the Impossible podcast with none other than Craig Venter of many different fames, but we're going to talk about a couple of them in particular, including mapping the human genome. Craig is local here in La Jolla. He has his institute named after him down the road from our campus, and he's graciously agreed to spend some time with me. I'm going to run out of time before I run out of questions. Craig, thank you so much for visiting.
My pleasure to be here.
And you're a proud alumni, son of San Diego, UCSD. And we're going to talk a little bit about how the campus has changed a little bit. But sitting in that chair a couple of months back was Kim Stanley Robinson, who also goes by his middle name only as Stan. I don't know what it is with you super famous, brilliant, creative types. So today we're going to talk about a variety of subjects, including your recent book, The Voyage of Sorcerer II. We're going to talk about what happened to you on Sorcerer I, which is foreshadowing. But first, we're going to start with a very simple, easy question, Craig, and that is the one posed by Erwin Schrödinger in the 50s in a monograph, a very slim monograph. And that question was, what is life?
Well, it's a book I recommend that every scientist read at least once. I've read it a few times. A few years back, I was asked to give the only time somebody was asked to give the Schrödinger lecture other than Schrödinger in the same hall under the same circumstance. It was really an amazing experience. And because we've designed the first living cell, that didn't happen in nature, people assume that I can answer that question. But he tried to define it in physical terms and thought about things about the genetic code long before Watson and Crick. And while everybody was sure that it was proteins, he said it could be as simple as Morse code.
Crystal.
And I was talking to Francis Crick about that. He goes, well, that was obvious to everybody. He was very dismissive of, that was hardly a unique notion, other than from protein chemists who still refused to give Avery the Nobel Prize for proving that DNA was the genetic material. Cells are very dynamic, changing second to second. But one thing is fundamental to all life, and that's the genetic code. If you take the genetic code out of any cell, any species, the cell dies very rapidly. The species dies. That's why we're so susceptible to radiation poisoning. It basically blows apart the DNA structure, and you can't continue to produce proteins and live. So some proteins have a half-life of seconds, some minutes, some hours, but they're not permanent structures. So every cell in our body is second to second constantly being rebuilt. So the genetic code is being read, translated, and proteins produced on a constant basis. It's even coded in the protein how long they'll live and their degradation rate. So it's a constant synthesis, degradation, taking out the garbage. And so without the fundamental information molecule, there is no life. That's a good fundamental start. Cells, have to defy entropy. They have to keep existing by creating energy. They take things from the environment. We have hundreds of ways that different cells make energy, and the forms of life vary from things that live at 135 degrees centigrade down to sub-zero temperatures. History of biology is it got defined in a human-centric point of view. So, we were the standard, so nothing could live out of 37 degrees, and we were the center of the universe. We're not the center of biology. We may be the center of trying to understand and interpret biology, but we're the minor species on the planet. Key proteins in the membrane pump nutrients in, pump waste molecules out. But it's a dynamic system that, in my view, kind of spontaneously happens. Mm-hmm. And we're trying to see right now if we can get it to happen spontaneously. When we made the synthetic cell, we wrote the genetic code, and we developed a transplantation system where we could put that chromosome in a recipient cell that could read that code. And it read that code and then totally transformed that cell into what was defined by that code. So you change the genetic code, you convert one species into another. We're trying to now see if we can do that in a cell-free system to get spontaneous formation by having all the components together. So that's a long-winded way of saying we can't define life yet.
Yeah, I've had on multiple people, including Carl Zimmer, who from the New York Times and other venues I'm sure you've interacted with. I've had on many people discussing the origin of life, shadow biospheres, and everything, but never anyone who's claimed to create life. And it reminds me of this joke, which you probably heard before, but a group of scientists from JCVI, go up to heaven and they say, "God, guess what? We've created life. We've created life in the lab. We can make a man out of dirt." And God says, "Oh yeah, well let me see you do that. That's pretty impressive." And so the scientists over there, they go outside, they scoop up some dirt, and God says, "Hold on a second, get your own dirt." Meaning that you're starting from some base material. Now, obviously, in the origin of life studies, again, there's almost no real well-defined kind of pathway or definition even of how the origin of life came to be. We'll talk about my favorite way, which only explains how life on Earth got started. It's called panspermia. We'll talk about that in a minute because I'm very interested in that and your thoughts on that and aliens and all sorts of cool, fun stuff. But the synthetic life, it's rare in a career that you have one big hit. I mean, you've had hit after hit after hit. Talk about what was the genesis of that? Was there a sophomore slump fear that how do I top mapping that? First of all, you didn't only map the human genome. You made the first complete genome map of what's the name? Just
Haemophilus.
Haemophilus.
That was in 1995. So 5 years
almost
before
30 years ago. It's coming up on the 30th anniversary.
And that developed the tools that made me know that we had a new way to do the human genome. It was new mathematical algorithms for assembling the genetic code from the sequences that we'd get.
If we wanted to do that, if you started from scratch and we took you away, we put you on an island, with some collaborators, brilliant people, computers, centrifuges, PCR, et cetera, how fast could you do it today?
So,
and how cheap could you do it?
Yeah, it took us 10 years. Writing the genetic code is very complex. The machines are slow. We had to develop error. They're not accurate, so we had to develop error correction methods. You can only make pieces so large in size, and so we had to make multiple of those and find ways to link them together. As you make larger pieces of DNA, it gets very brittle, so you can't pipette it or do normal things. So we had to develop new techniques of putting it in gels electronically and moving it around in the gels. So everything we did, we had to develop from scratch to be able to do. But the rate of synthesis was very slow. And the other problem was in the final minimal cell, about a quarter of the genes are of unknown function. They're essential for life. You take one of them out, the cell dies.
This isn't junk DNA, what they call junk.
The only junk DNA is in my colleagues' brains. And that's one of my pet peeves. People come up with these overly simplistic, basically stupid ideas, that the part doesn't code for proteins must be junk.
Right.
And so I offered several of those people to surgically remove their junk DNA and see how long they lived, but there were no volunteers. But the problem was we tried to design life on first principles based on what we thought we knew about biology, and it proved to be impossible. So the reason it took so long, in part from the slow methods for synthesis, became trial and error. We had to add genes back, then see what of those we could remove until we could get a living cell. So we'd add back a bunch, and then we'd get life. And then we worked out, we can remove some of those. We had methods for knocking out genes so we could tell which ones were essential and which ones weren't. But so it was basically a trial and error process. And I think the biggest finding, and it's similar to what we found with the ocean microbiome, is science reaches plateaus of knowledge, and the geniuses in the field sort of trying to define things as though we know everything. I mean, I'm sure it's happened in your field multiple times.
Absolutely.
So protein chemists thought we knew all the protein folds, we knew all the protein families. It was going to be hard to ever discover anything new in the ocean.
Just stamp collecting.
In the ocean, they thought there was only a handful of different microbes. And like proving junk DNA is not junk, instead of that being a major finding, you're disproving some idiot's stupid statement, calling it junk DNA in the first place. The Challenger expedition that we followed, it was from the 1870s. It was the first true scientific expedition in the oceans. Was sending a dredge down every 200 miles to see what was on the bottom of the ocean. And again, the brilliant sayers at the time said there couldn't possibly be any life below 1,800 feet.
Arbitrary.
And so when they discovered life at every depth, including they discovered the Mariana Trench and life at the bottom
Smokers.
of everything. So it was disproving, again, an idiot notion. I mean, there's discovery science. We showed discovery science is not dead by you can go out, ask questions, and make more discoveries. Science is limited more by this dogma that gets set up of inane ideas that if people really thought about it, they wouldn't come up with them. Before we sequenced the human genome, people were arguing that there were hundreds of thousands of human genes because there had to be a gene for each trait and function. I mean, it just shows how little was even fundamentally understood about what a gene does, what a protein does, and that it wasn't combinations of effects. So the biggest finding is we found 20,000 some odd genes instead of hundreds of thousands. But it was only a surprise because of the silly notions that were out there. If they weren't there, it would have been, that makes sense. 20,000 combinatorial is a huge number.
Yeah.
Genetic technologies, including gene therapy and synthetic biology, are surrounded by ethical, social, and safety concerns. However, despite being controversial, they offer promising opportunities to revolutionize medicine, improve personalized treatment, and tackle various challenges of human life. So it's essential to stay up to date with the latest developments in this exciting field. For instance, recently the FDA approved the very first treatment to use the gene editing tool known as CRISPR, which my wonderful guest on today's episode, Craig Venter, talks about. They just approved it. But the media landscape surrounding these developments is often fragmented, making it hard to find reliable information and find a balanced view, which is personally why I love Ground News so much. I even deleted the iPhone News app that's default on my phone and replaced it with Ground News' widget app, and I also bought it for a present for my older brother Kevin. Ground News is an app and a website that gathers together all the world's media into one place so readers can compare coverage and see the full picture of what's being reported worldwide. For every story, you get a quick visual breakdown of the news outlets reporting it, including their political bias, how factual the source is, which entity owns the source, and which countries are actually reporting and covering the story. For example, let's return to the FDA's approval for the first CRISPR treatment. Right away, you can see that 162 news outlets have reported on the story. Of these 162 outlets, 23% lean left, 11% lean right, and an overwhelming 66% come from the center. You can even see who owns the outlets reporting on the story.
63% are media conglomerates.
Ground News also makes it easy to compare the headlines to see how the bias might shape
and influence the framing of the story and affect our understanding of it. One of my favorite features of Ground News is the blind spot feed, which allows you to see stories that are underreported by either side of the political spectrum. Ground News lets you get a deeper understanding of the complexity and nuance of different issues by identifying media narratives and their biases. You can see every side of the story and thus develop a well-rounded worldview, which is pretty substantial in these turbulent times. You get access to newspapers and things that are very hard to find. Go to ground.news/Dr. Brian to stay fully informed on breaking news and compare media coverage. Sign up or subscribe through my link for 30% off unlimited access if you support the mission, and find it as essential as I do to scientific literacy. When we think about unsolved problems in physics, there's the classic notions of these grand kind of prizes and so forth that people will stake their whole lives and careers on. Famous one, theory of everything. Can we find a single equation that's maybe 1 inch long that you could write that Einstein was unable to do? And of course, going back to Schrodinger came up with this famous paradox of the cat, Schrodinger's cat, the superposition of living and dead states. And that was meant to sort of reveal and crystallize what he thought of as a paradox in the interpretations of quantum mechanics. Are there similar problems? In other words, like, he would say things and Einstein would retort back, does the moon exist when I don't look at it? And all sorts of, God doesn't play dice, obviously, is a famous one. Are there interpretations of biology? In other words, it's not clear that we know that there are only 4 fundamental forces of physics: the strong and weak force, electromagnetic force, and of course gravity. There could be other forces. Sometimes they're called fifth forces, but we can't rule them out. And it's sort of an interpretative or philosophical question. Are there philosophies of biology in terms of interpretations? Like, could there be genes that we don't know what they express or what they produce because we're looking at them through how humans are currently? Could there be something like some sixth sense that humans have, like polarization of light? Are there genes that would trace, the sensitivity of polarization in certain individuals that we just don't know about because maybe we only discovered polarized light relatively recently? It's a long-winded way of asking, are there issues in the interpretation of genetics and the human genome?
Well, totally. Even starting back, as you said, with the origin of life, the assumption that exists everywhere in biology is that everything gets back to a common origin. That means if there was panspermia, there was only one event and everything in the biosphere came from that one event. I've always just fundamentally thought that was bull. It just doesn't make sense. Mm-hmm. And as you know, the fundamental chemicals of life are found universally.
They're on this table over here.
They're found on every asteroid that things are measured on. In my view, is every place you have the same fundamental components, we will fundamentally get life. My bumper sticker says life happens. And so I think there were thousands, maybe millions of origins. There's competition for these, but to assume there was a singularity event, I think is just extremely naive. And
what is the most plausible in terms of the extant versions of not just origin of life on Earth, which is a huge problem to solve, and we have Miller-Urey as on our campus, literally a foundational experiment, which is not currently accepted, as I understand it, as representative of the oxidizing and reducing conditions of the early atmosphere.
It was a cool experiment.
It's a very cool experiment, and that's super fun to talk about. But that would only, and again, forgive me, when I used to do biology experiments in high school, Craig, we'd get a frog and we'd have to dissect it, and my frog would not even die. I was horrible in biology, so I know almost nothing about it. But that would only solve life origins on Earth. But what is a plausible, in your set of ideas for origin of life in the universe as a whole?
So in my second book, it's called Life at the Speed of Light, and it's based on the one invention I'm proud of. It's a biological teleporter. It's called a digital biological converter. It was based on the notion of that we can send the genetic code through the internet, through electromagnetic waves, any combination of things, regenerate that code and regenerate life. And the notion was we can send a DNA sequencer smaller than this coffee cup to Mars or other places. And instead of sending up a $5 billion spaceship to fly back a sample taken from the subsurface of Mars, we can send a sequencer sequence what's there, send the digital information back, and we can recreate the Martians easily here in a laboratory using the tools of synthetic biology. So it's not the Star Trek teleporter. It's sending the digital information for life, but because that codes for everything, it can be recapitulated. My understanding is we exchange about 100 kilograms of material between Earth and Mars annually.
That's right.
So various calculations, you can't take a shovel of Earth soil without having Martian soil in it. And so that means when the oceans existed on Mars, and some evidence is they still do on the subsurface, that we will either still find living organisms, and they'll very much resemble what we have here.
That's a meteorite found in Argentina, but behind you, somewhere else over there, I've got a sample of a lunar meteorite, which obviously hit the moon. That's your gift, by the way.
It came here. Oh,
and
that's
came
fantastic.
here. So the converse is also true. We're exchanging medium with Mars.
So when life is discovered on Mars, it will resemble life that we discovered in the ocean voyage. And microbial life and viral life will, in my view, be ubiquitous in the universe. Now, there's limits. We can't go right now above 135 degrees centigrade, but we wouldn't last too long at that temperature, personally. And we have microbes that live in very high doses of radiation, Deinococcus radiodurans. The space station was coated in part with that to see how long it would survive, and survived a long time. In fact, one of the stories that I tell that got the NASA director very annoyed with me, I said the outside of the space station is covered with shit. And it literally was, because early on they just pumped out all the human waste outside, and a lot of it stuck to the outside of the space station. Now they pack it into stainless steel containers and launch it back into the Earth's atmosphere. So I tell people to be very careful when they wish upon a shooting star. That may be the wrong one. So life will live in space. It'll live on the surface of these things. It will live in nuclear reactors.
And geysers.
So trying to extrapolate from human biology, we say, well, of course it can't exist in other conditions. The only reason I'd like to live a long time would be to see it proven that it is ubiquitous and is everywhere we look.
Hey there, fellow voyagers into the impossible. It is I, your fearless host, Professor Brian Keating, here with a microscopically tiny request before we go back to exploring the potential of biotechnology and its ethical implications, and that's to make sure that you're all subscribed to the podcast. I did some research and number crunching of my own and found out that only 18% of you are actually subscribed to the channel of all those that watch it. And to make matters even worse, only 8% have notifications turned on. You're missing out on so much great, amazing, and free content. So make sure you like, subscribe, and turn on notifications. I know you hear it from every single YouTuber on Earth, but to get the greatest possible guest on this show, I really rely on that, and it will help me help you. So do it. Do it now before you forget. It just takes one little push. Now, back to the episode.
So the thought comes to me, when I read Life at the Speed of Light, that, that does involve a much slower process than the speed of light to transport the 3D printer, the sequencer, et cetera.
Well, you have to get those there, but the data can come back at the speed of light.
So I guess the obvious implication that I'm kind of drawing from this is that, well, maybe there were other civilizations and species and so forth that created some kind of sequencer, which we call DNA, and that produced us. What are your thoughts about, it seems that DNA, which you're, at least as big an expert as exists on the planet today, that it could be the most, kind of basic evidence for extraterrestrial, not only existence, but intelligence. Am I off here? I mean, it's durable. It's like, I've heard of this Long Now. Have you heard of the Long Now Foundation? Yeah. So they're trying to build a 10,000 year clock, like Stuart Brand and Kevin Kelly. So 10,000 years is child's play compared to how long DNA has lasted. So what are your thoughts about that as a signature of ETI?
When I was the first human genome sequenced, And when that sequence was finished, to show people they should not be afraid of their own sequence, it was put on the internet. It's been, broadcast. So my genome's been broadcast into space now for 25 years. So,
Who knows what's coming?
it may come back, and, a troop of Craig Venters may come back and land here because it can be recreated from the sequence. But it's like human cloning. You don't get the same answer every time, other than in the basic structural and functional components. We're still plastic individuals and can be modified, and we're sending data into space constantly. People could be sending it to us, and we're not yet knowing how to interpret those signals that are coming in.
And the fact that it lasts so long and has this durability and resiliency is just so striking. And I don't think there's anything that's creatable in a lab that has any, that you can create or that has been discovered that has the durability of something like that, that's capable of being produced by a mind, by an intelligence source. Now, obviously, that brings up notions of all sorts of things. Like, if you were to construct the most likely evidence of life traversing the universe, it would be something that traverses at the speed of light, given the vast distances, which kind of brings me to my next question, which is about artificial life forms. Not the kind that you synthesized, but necessarily artificial life, artificial intelligence. And the question I have is really, would it make sense to teleport, even these, 3D printers or even the code, which still has to rely on matter, which cannot travel at the speed of light if it has mass, versus pure information? So,
but that's what DNA sequence is. It's pure information.
Right.
And so that could be sent anywhere. And certainly short distances, it would be the fastest way to get anything back from Mars or Europa, any place else. It makes it feasible to do that instead of waiting for a round trip of physical material.
Right.
It's the fundamental chemical components we just talked about are basically ubiquitous every place somebody looks. So having DNA form, RNA form is extremely likely. And once it forms, it can accidentally code for something, or it can very specifically code for something. So in the first synthetic genome, we created a second code. It was based on Isaac Asimov's rules of robotics. We decided, being the first one to make a synthetic organism, that it should be watermarked to clearly distinguish it as a human-made organism.
Deep fake.
Versus, otherwise it could really confuse everybody doing evolutionary studies, for example. So we created a code. People have used ASCII code, but that creates problems. So we created a unique code that puts very frequent stop codons in. Because, for example, we could write your name in the genetic code with this code, but without the stop codons, that could lead to a new protein, a toxin, something of very unintended consequences.
What is, I'm sorry to interrupt, but what would be the likelihood of that? It seems to me, if I go into my friend's Tesla and I start to, play around with the code, almost anything I enter into it is going to destroy it. It's less likely that it's going to produce, something new and functional, or just an old fashioned Dodge, Wrangler or Jeep Wrangler, go in there with a hammer and start playing around. More than likely, unless you do something cosmetically, you're going to make it irreparable and possibly non-functional. So is that I appreciate the ethical concerns, but is that really probabilistically likely?
I think there's a high probability of that. All the microbes in the environment are basically chemical warfare with each other. That's how we're discovering so many new antibiotics. So they create antibiotics to deal with these chemicals. They're randomly evolved from just, the biggest drivers of evolution in the ocean are UV light and oxygen. And that's why there's such a high rate of mutagenesis. When you're doing this experiment 100 billion times, anything's possible.
Yeah, so that brings me to, some of the questions that naturally spring to mind. I mean, the potential for novel uses of it, incredible. Potential for, we just endured this 3-year pandemic, right? So what are some of the concerns that you have beyond the, it could do something unintended? What about the intentional misuse of this technology?
So it's one of the concerns that we had. Any virus, any bacteria that's been sequenced, any pathogen, we could readily reproduce. I think my friends in China don't like me to say this, but I think Occam's razor says you have to prove that COVID wasn't a lab-made pathogen.
Yeah.
Could have come out of the market, but 3 people got sick there. They could have gone to the market. So, their alternate hypotheses aren't impossible.
Right. Or they could have brought it to the market.
It could have come from an animal, but NIH, under Francis Collins' direction, was funding gain-of-function research in this lab in China that we had no control over. I mean, it's the most unethical, thoughtless idea that I can imagine.
Sorry to interrupt, but I have to just why was it done in China, right? Because they couldn't legally get it to be done here, correct? They couldn't do gain of function research. It was forbidden.
They could definitely do it at CDC and the spacesuit lab where we grow smallpox and everything else. And so doing it in a lab where you have no control of the use or the outcome or the processes, the fact that 3 people got sick from the research there says something wasn't being done right, because in the P4 facility at CDC, they grow the worst pathogens on the planet. And we sequenced the smallpox genome as part of an international treaty. It was growing up in the spacesuit lab, and they would only send us about 1/3 of the genome at a time to sequence, so we would never have the whole thing. But it would be easy to recreate just from the genome sequence now. Mm-hmm. So we do have to be concerned with that. People created the notion of designing new pathogens. That's much more difficult, in part because we know so little about biology. I mean, the fact that we couldn't even design a living cell because of all the unknown functions out there essential for life. I mean, nobody would have predicted that. Not a single person in biology would have predicted what we found.
That's amazing.
And it just shows we're missing at least 1/3 to half of all biological knowledge yet to be discovered. Gain of function is changing 1 or 2 genes to try and make things worse.
Not necessarily. Sorry to interrupt again, but when I had COVID, I understand you had a horrible experience with COVID, but I had a relatively benign. In fact, I lost 10. I dropped 5 pounds from my double chin to my stomach. No, I lost weight. I didn't have smell and taste. And, it's been more or less permanent. Yeah. But imagine, and God forbid, I'm not suggesting, it was really good because Brian Keating lost 5 pounds. There's more to come, right? But the question is, Craig.
But you were vaccinated.
I was vaccinated. Yes. Yeah, it didn't prevent me. Yeah. Somehow my wife never got it, and she's exposed to a bunch of kids. But the question I have for you is, there could be not just, there could be positive uses for gain of function, right? Not just negative or weaponizable.
It's important for leading to understanding, but you got to do it under the right conditions and the right safety environment and places where you have control. I think there's reasons to potentially do it, but you want to do it the right way. With smallpox, which I get very familiar with, not only sequenced the genome, but once I sequenced it, it was supposed to be destroyed. And I convinced the government that they should not destroy the stores of smallpox. They're still in the safe at the CDC. Mm-hmm. It's this little tiny old-fashioned safe from the 1930s, I think.
Great.
Because I said it creates a false sense of expectation that we've rid the planet of this pathogen when it could be reproduced very simply. I went and gave a lecture to President Clinton and his entire cabinet on this. Mm-hmm. And this was even early days before we really had all the synthesis technology that we have now. Mm-hmm. But because the smallpox sequence was so closely related to vaccinia, which we use as a vaccine against smallpox, just doing site-directed mutagenesis, a diligent team could convert vaccinia into smallpox. Now we could just synthesize it from scratch. These are not, ubiquitous methods. There is a reason that in the last 14 years, no other lab in the world has been able to make a new life form like we have. It's expensive, it's time consuming, it's not things governments fund, except maybe in China. But we also had an expert team of 20 scientists, including 3 National Academy members and a Nobel laureate, and just some extraordinary people working on all aspects of this. So teams like that don't get put together very often in science, especially spontaneously and self-funded. But there are new tools coming. We're working with a company called Avery that is doing DNA synthesis on computer chips, where they can make a different DNA molecule on each pixel on the computer chip. Just by changing the voltage on that pixel, they can do deep reduction, change the chemistry. And so that could be a 10,000-fold increase in our rate of doing synthesis, which means even though it's a trial and error process because all the unknowns, instead of making one molecule at a time and testing it, which was hard and time consuming, we can maybe make 1,000 different chromosomes, and your screen is for life, which one gives you a living cell. And so it will change the experimental rate for doing things, hopefully for the betterment of mankind. But every time there's a breakthrough in technology, you have to worry about the dark side. So my organization created a robot for assembling DNA. The notion would have been from the digital biological converter, it just take in sequence information and make a DNA or protein molecule. And it could do that, but we set it up so that the code could not be changed. You had to order the prerequisite oligos from us.
So you
They'd be in a tube. I designed 10 different safety devices into it that if somebody tried to modify it, it would shut down the machine. Nobody else is doing this kind of stuff in science or even thinking about it, but we're trying to think ahead on it so the devices we're creating for basic science didn't turn into weapons manufacturers.
When I look at your career, and you already mentioned Isaac Asimov, who is one of my big inspirations. Obviously, this is part of the Arthur C. Clarke Center for Human Imagination that I'm the associate director of, and I should thank Eric Veary, the director, for reintroducing me to you after a decade of not seeing each other. And that is, of course, Sir Arthur C. Clarke's visions and pronouncements and so forth, that some of which came to be science fact from the realm of science fiction. And I wonder, what seems like science fiction today to you that could be a grand challenge akin to mapping the genome, to making synthetic cells? What is the next frontier that seems, again, like science fiction? We already agree that, making pathogens and so forth, that could be, that sort of could happen now. God forbid it does, and affects the planet. But tell me, like, what in your wildest dreams, where do you go from here? What is a science fiction fantasy for biology?
A brief interlude before getting there. The same tools that are used for making potentially pathogens are being used for creating the countermeasures. So biological warfare wouldn't be a threat if we had a repertoire of antivirals, antibiotics, vaccines to deal with it. And so we created the first, using the digital biological converter, the first FDA-approved synthetic DNA vaccine. And it was made against a flu strain that was discovered in China that looked very pandemic potential. The Chinese sequenced it and just posted it on the internet. We downloaded and made the virus in a week. We were the only source for the CDC and pharma companies of this virus because China wouldn't export the biological molecule. But it just shows you don't have to. Now you can just send the information and recapitulate it. And so we did a test. We set up a device at Novartis. We sent the sequence to them. The device made the molecule, and they scaled that up for vaccine production. But everything that happened with the COVID vaccines were really modeled after our early success. And you can make large number of RNA molecules now, and so our model with that, contributed to all of us getting vaccinated against COVID. But to answer your question on the long distance horizons, the short distance is going to be the potential for totally new industrial revolution of, for example, all the microbes we discovered in the ocean. They make chemicals more complex than the best chemists on the planet can make. And so taking those gene pathways, putting them in synthetic organisms, we'll be able to create whole new chemical libraries that will change every type of chemical therapy, but also industrial chemicals for building things, making things. And the notion of this was developed for ideas on making things on Mars instead of sending everything up there, because it's very expensive to build enough rockets to carry everything up there. So if you can get microbes to produce the building materials and the chemicals and the food substances, that would be the future. So I think that's the near-term future. I proposed, because, while I believe panspermia has happened and is continually happening, we've already contaminated the moon. We've already contaminated Mars. You can't truly sterilize things here on this planet in a microbial world where there's viruses and microbes in the air, just everywhere you are. You can't eliminate them. And so we've sent microbes to Mars. We've sent, people in poop to the moon. We're pumping things out of the space station. So we're creating a version of panspermia. Every astronaut that goes up to the space station takes a totally different repertoire of the microbiome of millions of different bacteria with it. We've sequenced the HEPA filters from the space station. They're loaded with so much diversity and so much stuff. It's just stunning. But I've argued that any astronauts going to future planet colonization, we should sterilize them first and give them a synthetic microbiome, so we're not creating a set of new pathogens that would develop in an environment. So those are sort of short-term ideas. Human genome engineering is inevitable. Yeah. We're not ready for it now. We understand 1% to 2% of the genome at best.
When you say understand, what do you mean?
Know what these genes code for, why you have the traits that you have, why I have the traits that I have. We just had this recent discussion here about imagination. I have aphantasia, so I don't see any pictures at all in my mind. I only think in concepts. The person I was talking to only sees in pictures and puts his world together through pictures. Wow. And we don't even know the simple basis of that, because NIH doesn't like to fund behavioral studies that lead to social changes on the human brain. So we're just not studying it. You can't understand bases of what's called intelligence, not that, but there's multiple
Proxies,
different types.
right.
It's a spectrum of things. So we're at still a very early stage of understanding. One method of survival of our species is going to be to engineer humans to live in environments that will be inevitable because we're destroying slowly the biosphere that we live in. So maybe it'd be humans that can tolerate higher levels of CO2 or lower levels of oxygen.
Higher temperatures.
Or higher temperatures. Once we don't even have a preliminary understanding of the brain. We think we do because we understand more than we used to, right. So that seems like huge breakthroughs, but we basically understand nothing. Right. And we certainly don't understand the genetic basis of how the brain is hardwired. So in inbred mice and rats, the neurons are in the exact same location in the brain, plus or minus a few microns. So all that's completely under genetic control. So we start out being hardwired, but we're also hardwired to be plastic and adaptable. That may sound like a contraindication, but it's part of the design.
Anti-fragility, yeah.
To be adaptable, and our brains are plastic to a certain extent and can change structure and function, but we're not really studying that because we don't know what most of the genes even do yet. So we have to increase our knowledge level before I would ever be willing to start engineering the human genome to change humans.
Interesting. Yeah, it's reminiscent of the mapping. We have a periodic table on the wall over here. I don't think I can capture the lanthanized, those are the noble gases. There it is in the corner over there. Most of these were discovered by number, in the last 100 years or so, and of course many of them are important for life, but actually not as many as you'd think, right? I think the highest one has some viability is like there's some amount of copper. Zinc obviously is important, but I don't think we need cadmium or technetium, etc. So there's a lot of wasted space.
Iron's very important.
Iron's very important, but it comes before copper, as I mentioned, and zinc. There's a little arsenic, and people have claimed they found arsenic life that went away pretty quickly.
Yeah. I
want to talk about an event. I think it happened in 1997. You were considering leaving this company HGS and going off on your own. It meant a great sacrifice for you financially in terms of stock options, things you had vested, important investors and relationships in the corporate setting. And you talk about, setting out to sea, to clear your mind.
Yeah, it was not 97. It was actually early 2000s.
Oh, okay.
So I'd sequenced the genome.
Yeah.
I raised $1 billion cash for 3% of a company with no revenue. I didn't get along.
This is Celera?
Yeah. Celera had a parent company, Plera, that was sort of a holding company, a very volatile Cuban CEO who only tolerated me because I was the only one who could sequence the human genome. But I indicated to a board member that once I was done with that, I was considering going back to my institute because I wanted to keep doing basic research. He panicked. They decided it would, if I left, the stock would crash. So they got the brilliant idea to fire me, and the stock crashed even faster. But went from the intensity of those years. You got an idea from the book. I was on the front page of a newspaper almost daily somewhere in the world. The world was watching every move. One thing I point out, there's thousands of reasons perhaps why I should have failed. Okay. But I had the best team of scientists in the world, and they were all motivated to make it work and make history. I was the orchestra conductor. It's the team that actually did it. Gene Myers led the algorithm team that wrote the whole new algorithm for assembling 25 million sequences that nobody else thought was even possible. If it hadn't worked, it would have been the biggest flame out in science history, right? I would have been noted for the fastest death in science from trying to do something too big and too bold. But it worked, but it was such intensity. It was a 24-hour day thing for 2.5 years, building this, then actually sequencing the genome. We didn't know, the White House event was scheduled before the computer stopped the calculation to know whether we had a genome or not.
Hey there, it's me again. Are you enjoying this incredible conversation with one of the most brilliant thinkers alive, Craig Ventnor? Then I know you'll love what I'm about to offer you. If you go to briankeating.com/list and join my mailing list, you will get the hottest news in the cosmos, from consciousness in the brain to life in the universe. And that will make you the star of any cocktail party. All this for free. My weekly Monday Magic mailing lists always consider the highlights from all around science and especially from the Into the Impossible podcast with links to transcripts and giveaways. And you may also win a real piece of the early solar system, maybe the piece that brought life to Earth in a panspermic voyage across the cosmos. So do yourself a favor and go to briankeating.com/list and join now. That's briankeating.com/list. Now back to the episode.
Take us back to that because we're going to get to the Voyage of the Sorcerer I, I believe. But talk about the race. Talk about you, Francis, NIH, public-private, partnership, rivalry, and then winning it.
Well, I've gotten lots of attention. I've got walls full of awards, including the National Medal of Science from Obama for that work. That I had to share with Francis Collins, but it's all right. So, I approach things pretty much as a basic scientist asking questions. So I was trying to isolate the adrenaline receptor, work that started when I was a student here at UCSD. And the standard in science then, before genomics, was you'd spent 10 or 20 years trying to isolate a protein and characterize it. Lots of Nobel Prizes have been given for single protein discoveries. And so when the first discussions in the mid-'80s came of the idea to sequence the human genome, which everybody thought was outrageous, I love the idea, after spending a decade trying to get one protein, the thought of just having all the neurotransmitter receptors and everything to do with cognition in one step instead of waiting 4 centuries to do it. It was just a sexy idea to me. I had the first automated DNA sequencer because I was an intramural at NIH. I had more money than God to do whatever I wanted to do. So I actually sequenced the first genes in history with automation. And so I had the only tools to actually do what was being proposed for the human genome. I just got very excited about the idea. And randomness is a key theme in mathematics and cosmology. And
serendipity, yeah.
It's also a key part of what we did in genomics. So shotgun sequencing is you have to have a perfect Poisson distribution of clones, and then you randomly select those and sequence it. And by doing that, you can recapitulate the entire genome. If it's not truly random, you can't do that.
Can I just ask, when you say sequencing, so I'm envisioning, this process, running and sequencing different, pairs and even individual base pairs, et cetera, within the gene, right? And then
the machine spit out roughly a 500 base pair sequence of DNA.
That's what I was going to ask. So what was the fundamental atom of that?
Yeah.
So okay, go on.
So we had 25 million fragments, roughly 500 base pairs long.
I see. Okay, continue.
And so that's the mathematical problem that had to be solved, putting that back together. NIH refused to fund the grant that Ham and I submitted in 1995, this idea we had to sequence the first genome.
Yeah.
And even after we had it 90% done, we took money out of our own bank account at the Institute to do it. It was over 90% done. I wrote a letter to Francis saying, look, it's clearly going to work. I'm not trying to embarrass NIH. If you fund it now, you can still share the credit for doing this. Mm-hmm. And he wrote back, I have the letter, I think it reproduced in my book. He stood behind the study section who said, this is impossible, it won't work. A few months later, we announced the first genome in history. Yeah. And so that sort of created, a tension because I did it outside the realm of this entire enterprise called the Human Genome Project that was starting with a 5-year project to sequence E. coli and then yeast, and they were going to progress up to nematode, then Drosophila. Yeah. And I kind of threw a monkey wrench into that because E. coli had barely been started, and we did the first one independently. And if you read the science paper in 1995, I had to really fight for this line to be in there, but I said that I believe this is the method that will be used to sequence the human genome.
Right.
I was probably the only one on the planet who believed that idea. But, comes with maybe the aphantasia of being able to think in concepts. Some things are just totally obvious to me. And fortunately, a combination of great intuition and that ability to put concepts together. The only time I screw up in life is if I ignore that intuition. It's been right 100% of the time. And NIH, just refused to fund these experiments to see it. They had their, it was a public works project. They were distributing billions to
100 campuses,
to labs around the world, and led Cindy Brenner to joke, why don't we have prisoners do this? If it's a forced labor thing to do, but it made sense to solve it mathematically, and so we sort of gave up and thought that I was going to have to sit on the sidelines. I got a call. In fact, I got several calls. I treated them. I thought they were junk calls, and I ignored them. Of offering me $300 million to start a company to sequence the human genome. Wow. And it was Applied Biosystems, the company they were making a new capillary sequencer that they thought would fit with my method.
Do these rely on PCR? And maybe you can explain. Okay.
No.
Did you know Kerry when he was?
I knew him well.
Okay.
Yeah.
What was he like? Just a side. Could we take a sidebar here? He came up. Well, first, could you explain what PCR is and why it wasn't relevant? To a knucklehead
Well,
like
PCR
me?
was a method for, it's like a Xerox machine for making copies of DNA. It was really a profound technique that changed what people could do in the laboratory. He's a genius, but really a crazy mofo.
Tortured genius. Yeah. Well, he's a wild genius.
He's a fun guy.
Yeah.
I enjoy him, and but he went off, with bizarre ideas of HIV and other things in the end. But we use components of PCR to make copies of the strands of DNA that were going to be sequenced. So we had rooms full of PCR machines that were part of the process of getting enough molecules of DNA that the automated sequencing machines could read.
And those were the capillary things that Applied was going to give you.
So, they sent somebody out to see me and said that they were sincere about the $300 million and wanted me to start a company, and invited me out to Foster City to look at their new machine, which was actually 6 breadboard devices spread over 6 different buildings. And I looked at all of them, and I looked at the preliminary data, and it was totally clear to me that it was going to work. So we did some calculations of how many machines it would take to do this. And it was funny. We made an order of magnitude error too big. And so it looked like it was going to take 30,000 machines. And we were sort of saying, well, this still might be doable.
Brute force.
And then we discovered there was a tenfold error. And I was, in fact, it was a 100-fold error because we only needed 300 machines. And even though that was absurd, all of a sudden, by contrast, that seemed so doable. We thought, okay, 300 machines and $300 million, we can do this. So I flew back to my institute. I went to see my friend, the Nobel laureate Ham Smith, who'd been working with me for 20 years. And I said, look, I looked at the machine. I'm certain it's going to work. If we get 300 of these machines and scale everything up, I think we have a shot, and they're giving us the resources to do it. He goes, I don't think it will work, but I'm going with you.
That's a shot.
And that's sort of how the whole team built. As soon as I announced it, we got 1,000 applicants of the best scientists in the world, the best mathematician, physicists. We had to build the 3rd largest civilian computer in the world, a whopping 1.5 teraflops, which cost roughly $100 million to build, and now it's a few $1,000 computer. It's kind of
GPUs.
Cool how fast things change, but it worked because of the dedicated, incredible team that I built. I don't think a team's been built like it before or after. Ham's complaint afterwards was, it was such a unique experience. we did it too quickly because we sequenced the genome in 9 months, and then just
gave the illusion that it was a simpler than it was. Right?
Things exploded. But so the intensity of this was so much. When I was fired from there, it was just like going into a sensory deprivation tank. And so I decided I had to do some recouping before deciding what I was going to do next. So I got on my boat and sailed down and lived in Tortola for several months, working on my boat and thinking of ideas of what I was going to do. Came back and started 3 new not-for-profit institutes, one to do the environmental work, one to do synthetic biology, and one to build off the ideas off the human genome. But it took that, rebuilding period, just, after anything that intense, when you're in the press every day, hounded every day, it was a very unique experience. Doing the negotiation with the White House. When I agreed to do that, my colleagues hated me for it.
They were jealous, or
no. My colleagues at Solera, because we were so far ahead.
Oh, right. Why give up why share the glory?
And scientists like Richard Lerner, locally, I had a dinner with him. I told him what I was going to do. He got viscerally angry with me. So people wanted me to embarrass NIH and the government for
maybe not embarrass
all the
them.
Horrible things that they've done.
Right. Well, they've certainly done. But tell me, do you regret it? If you could go back, would you have done that?
No, because it's the notion was, trying to be publicly minded with this. I mean, emotionally, would that have felt great to embarrass the hell out of them? That we did it with 100 million instead of 5 billion, and we did it in 9 months. My ideas got proven right, and the team got proven right, and I knew that if I didn't make the compromise to do the announcement at the White House, that the following year or two, when they eventually finished, they would do that, and we would be totally left out of it.
Right. It's like they say the third guy makes the money from the house. The first guy loses all the money. The second guy still loses money. The third guy sells it.
So it was a negotiated, truce, but it was really based on what Solera was doing. And I would get calls every day, as the computer run stopped yet, and because they were having to schedule all these dignitaries. It was on live international TV, right. And we didn't have a genome yet.
Sea change, yeah, I remember that very well. I was at Stanford.
But it got down to a game of chicken in the end, because I had to share my speech with the White House, because it was going to be live television from the White House.
You're not gonna.
And Tony Blair was going to be part of it because England was such a big part of the genome effort. And they sent me Tony Blair's speech, and it was just totally insulting, totally one-sided, praising the public effort and attacking this company that intervened.
Right.
And
venal business.
And I called the White House science advisor and said, unless Tony Blair changes his speech, I'm not coming.
Wow.
This was the night before the White House event. And he said, you're asking us to change a foreign head of state speech. We can't do that. And I said, well, I know you can and you will, if you want me to show up.
And they did.
He called me at 1:00 in the morning, and he goes, I can't send it to you, but I guarantee that you will be very happy with the changes that he's made. In fact, I was. He changed it 180 degrees so that all the scientists in England were totally pissed off with Tony Blair because he was being so nice to me. But, but these games, just shows the intensity of all this stuff.
And in the book, you talk about Francis, and there's a line that really resonated, shockingly so. You said something to the effect that he was more interested in the credit than the process or the money or anything. And that's kind of haunting, to think that there are people doing the science and it is truly, about them and about their egos and about their reputations. And you don't have to comment on it if you don't want it, but you did write it in the book.
But as you know, that's the history of science. There's been some of the biggest battles even early on here at UCSD with some of the big areas. You can't work at these levels without having a strong ego.
Yeah.
And so it's a question, what's the driving force? I mean, you want your ideas to be right, but we were still trying to do it in a publicly minded fashion. We're taking private money. We gave the genome away for free to scientists. I had a chance to embarrass the government. My view is they were embarrassing themselves. So we agreed to share the credit, even though it wasn't. So different scientists are totally motivated by different things. Yeah. We're given disproportionate attention, fame, than you can probably get in most other areas other than being a rock singer or something.
Yeah. But when it combines with power, I mean, I had on Jay Bhattacharya from Stanford, who's a good friend of mine, dear person. Of course, in late 2020, there was articles circulating around that there were fringe epidemiologists, including him and a Nobel laureate at Stanford, I think Levin, at Stanford, who had joined in, and we have to basically censor them or mock them, humiliate them so that they don't get attention. And one of the ways was to have op-eds in the Washington Post. And I found that really despicable. And it's not surprising when I reread your book, your Life Decoded, that was, kind of a character trait that I have to confess wasn't that unfamiliar from the way he is 25 years later.
Yeah. You can do good science and make good contributions, but your ideas as an individual can be really effed up.
Yeah.
And my quote friend Watson has proven that.
Is James Watson.
And he's now been censored by his own institution and fired, because I think he did make important contributions, not necessarily the role and the model of DNA structure, but he helped build Cold Spring Harbor and raise money and do things for it. He has contributed positively to science, but he's one of the biggest racists and sexists on the planet, and that does a disservice of almost counteracting any good that he might have done. And he's not the first one. There's other Nobel laureates that have really gone off on
Shockley.
Was again, sort of the predecessor there. Yeah. And just because people are bright in a certain area doesn't mean they have the right ethics and morals. And, when I announced I was going to sequence the human genome, Watson called me Hitler. And, that I was taking over things. But
he seemed directly threatened.
Yeah.
It's very scary.
Yeah. Well, because he was constantly afraid from the science they did and the discoveries that it would shut down Congress funding their program if it was going to be done faster and cheaper by industry. And instead, it was a very bizarre situation. And, we had the U.S. government and other governments competing against a startup biotech company in the United States. I guess the only one who would understand that at all is Elon, and he's done pretty good with his competition against NASA, but in part from learning from some of the things we did. China funds its biotech companies. It supports them.
Yeah.
Only in America would we have the government competing with a startup biotech company by outspending it 50-fold.
Or suppressing contracts.
And so it's bizarre stuff, but I guess that's the diversity of our system. The cool thing is I could have an idea like I had. It obviously stimulated others to give me the resources. They didn't do it in a selfless fashion. They wanted to sell their machines, and they made billions selling the machines because I made them work. Mm-hmm. But that's okay. That's capitalism at work. The net effect was I got to do first-class science for the public benefit and moved it along 10 years faster.
Yeah. Let's get to some fun science questions and actually some voyages. As you said earlier, the voyage of the Challenger back in the 1800s. Obviously, we haven't mentioned probably the most famous biological voyage until the Sorcerer II, which is the Beagle in biology.
Well, the Beagle was a survey voyage that had a naturalist on board that just went along to make observations along the way. So it wasn't actually a scientific expedition,
right?
But it's definitely the most famous vessel. And the observations that Darwin made are fundamental. Was that when you get life in isolated environment, there's evolution of unique genetic characteristics associated because it's an isolated environment. Mm-hmm. We see that today in human populations where there's been inbreeding. For example, Saudi Arabia was based on 12 Bedouin tribes, all first cousin marriages within the tribes, not even between them. Mm-hmm. They have some of the highest rates of genetic diseases in the world. Second, type 2 diabetes, only to the Pima Indians. Why? Because type 2 diabetes was a survival advantage for the Bedouin existence of feast and famine.
Right.
Once they switch to a steady society diet, it becomes a disease. Right. But it's locked in, and with the inbreeding, even worse. So Darwin's work totally predicted that in advance and what we're using today. But I had the pleasure of following his exact steps, only I had a new lens. I call it the lens of genomics. We could see things by looking at the genetic code after it was sequenced that he couldn't see even if he had good microscopes. Mm-hmm. So we discovered 10,000 times the life forms that he discovered, but they were the basis of all the life forms he discovered existing. But that's what happens. That happens in your field. You get a new telescope that can see further, new instruments. All of a sudden, the lens of genomics changed the entire world. Microbiology was based on what you could see through a microscope or what you could get to grow on an agar plate. Mm-hmm. And if it would grow on agar plate, it was deemed not to exist. And that's what started this expedition. They were discovering microbes in the ocean and numbering them one at a time. So SAR 11 was the 11th microbe discovered in the Sargasso Sea. And there was this paper by a physicist in PNAS that I read when I was on Sorcerer I recuperating, of how little diversity there was of life in the ocean. And as a lifelong sailor, swimmer, surfer, diver, this just didn't make any sense to me at all, because half the oxygen we breathe comes from the ocean, the diversity of all the food does. And that's where I got the idea just to use the same method we use for the human genome to try shotgun sequencing the ocean. Mm-hmm. And discovered just from the very first experiment where they had 11 organisms, we discovered 2,000 in just the first sequencing experiment and 1.4 million new genes. Wow. So we followed the Challenger. We took samples every 200 miles around the globe, over 65,000 miles, covering most oceans and seas. And even early on discovered more new microbes than there are stars in the universe, which made it easier to recruit physicists and mathematicians, because all of a sudden they said biology was a bigger problem.
That's exactly right. Yeah. Makes cosmology seem easy.
Yeah.
So that voyage began in what year did you start the first voyage?
Well, the early experiments started in 2003 and then really got going a few years later, where we did a full circumnavigation. But like everything in science, it wasn't as easy as just going out like Darwin did and taking samples and making observations. Darwin didn't have PETA, or he he would have been sued multiple times for the experiments. You know,
Tortoises.
when you discover the iguanas, he couldn't believe that they could breathe underwater. So he'd tie stones to them and throw them in the water and see if they'd survive. And
you don't do that with your graduate students?
Well, you can do it with graduate students. That's okay. But so we had to get permits. We had to work through the State Department with every country where we wanted to sample in their 100-mile border. It encountered numerous problems. We got arrested twice. We got threatened with sinking by the French and the British. We got boarded by a SWAT team in Australia. Just asking basic science questions in a world that's fearful of science is not always easy.
No, it is not. So is there going to be a next voyage of the Sorcerer II, or maybe even a Sorcerer III? What do we have to look forward to on the oceans?
Well, the good thing is, you know, when it's a simple idea, and most good ideas in science are pretty simple ideas, we showed that we could just take a sample from the environment, isolate the microorganisms. For seawater, it's simple. We just had a series of millipore filters that collect things at a very tiny level. So we collect the viruses on one filter, the microbes on the other, the diatoms on another. We just put the filters in the freezer until we could get to a port, send them back to the Venture Institute where we shotgun sequenced everything on the filter. It's an idea now. There's been hundreds of mini and major voyages copying this. Anybody listening, any kid can take a little vial, go out to the nearest stream, lake, river, ocean, estuary, take a sample, isolate the microbes, sequence them, and make more discoveries than were made in the 1900s of new organisms, because we have that much diversity out there remaining to be discovered.
Is there any way that they can actually submit them for analysis unless they...
Well, people have been putting more and more of these, the public databases, and in fact, it's one of the problems we're trying to solve with the synthetic cell. Most of the genes discovered by us and others are of unknown function. So we have now developed this catalog of biology on the planet without knowing the function of the majority of things that have been discovered. So we're in the infancy of science, not in a mature stage.
Well, Craig, this has been phenomenal, and there's much more to come. But what I love to do now is just end the beginning part of the conversation. I know you have a limited time here. I don't want to miss my audience questions. So what we're going to do is we're going to end the main episode of the channel, the conversation with Craig. And then in order to see part 2, or the question and answer period, as well as to hear Craig's answers to my final 4 existential questions on the meaning of life, advice to his former self, the most magical technology ever invented by man, and what he expects to give as a future sort of legacy for the planet. You'll have to subscribe to my mailing list at briankeating.com/list. And if you show me this little meteorite there, you will actually get a chunk of this rock. And we have some talks about panspermia, questions about panspermia in the bonus episode. So to get the bonus episode, go to briankeating.com/list. I will send it out to you as soon as it's ready, and you may even win a chunk of space rock. In fact, you're guaranteed to win a chunk of space rock. What I do, Craig, is anyone with a .edu email address who joins my mailing list gets a guaranteed fragment of this 4.5 billion year old piece of space schmutz sent to them along with its chemical assay. And we'll even put on some of Craig's DNA. I'm going to have him slobber over some of the meteorites. So tune in to part 2. You'll get the link when you join the mailing list. And for now, Craig, thank you so much for being a guest on the Into the Impossible podcast.